applications of what we learned about Monte Carlo simulation. We already can see that this formula is how we estimate the integral f of x. It's basically b minus a multiplied by the mean, where we sample x from the interval a and b, and the error is of the order of 1 over n. Like we already explained, you define your total number of points, you sample n, x from 0 to 1. This rand function automatically samples from 0 to 1, so you don't have to specify. But if you did .random.uniform, then you have to, for example, if I use the .random.uniform, then I have to say a comma b comma n, for example. But because automatically it does that, you can just let it be as it is. This is f of x. When you sample it, you just do f of x as usual. You take the mean. That's all. That's all. This one is the b minus a, because 1 minus 0 is b, because here you have b minus a. So it's 1 minus 0. You get the results like this. This is the estimated Monte Carlo. This is the exact. We used the SymPy library to do the exact and compare. The second demonstration is when we are estimating the area of a circle. Let's assume we want to estimate the area of a circle of radius 1. So the radius of the circle is 1. We want to put this circle in a box of length 2 and width 2. But we want to divide the length into -1 to 1 and the width to -1 to 1. Remember the formula we said? The area of the circle should be the number of boxes in points inside divided by the total number times the area of the square, because it's of length 2 and width 2. So 2 times 2 is 4. So 4 times n inside over n outside. N inside over n total should be the total, should be equals to the pi r squared, for example. And because r is 1, we wanted a unit circle, so you can say pi technically. And therefore, if we estimate randomly from -1 to 1, from -1 to 1, and set the condition that all values less than r should be counted as inside, and all that are greater should be counted as not inside. You can see here, you define the n total, define the radius of the circle. I'm supposed to use r equals to 1 here. I changed it. Yeah, so r equals to 1. In fact, here is supposed to be length equals supposed to be 2, width is supposed to be 2. I was testing some other things. So this is minus L over 2 to L over 2 is like saying -1 to 1. And so that's, I'm sampling from the width, I'm sampling from the length, and I'm setting the condition. If it is less than r, true. If it is not less than r, false. So I want to count all that are true. That ones that are inside, I will count them as true. So I define this inside, it will return a Boolean outcome. True, 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 false, true, false, true, false. Those that are inside will be counted as true, and else will be false. And then I count them. I just sum up all the truths. I get the area of the square, and I apply my formula. The area of the circle should be n in over total n times area of the square. So I try to compare with the real. This is just pi r squared. That's how it's supposed to be. I'm expecting the area of the circle we estimated using Monte Carlo to be equal to pi r squared. And this is if you want to plot, you declare the figure. You can, this is the inside, those that are inside, and those that are outside is like those that are not inside. This is telling you like not inside. So x values that are not inside and y values that are not inside, we declare them outside. And you can draw the circle if you want. This is just fancy thing, and this is it. So we see that the inside are the red and the outside are the blue. And here um, you can see that the estimated is 3.09, but pi is 3.14, because we expected that we expected it to be almost equal to pi, because pi r squared, r is 1. So how do you get to that? If you increase the number of, now we're somewhere around a trillion. If you increase the number, you may get closer to pi. Let's see if we can get closer to pi. Yeah, it's still working. I might have used maybe a smaller number. Anyways, we can terminate this and reduce the number of digits. So you terminate, you click on escape, then you click on I. You keep clicking on I clicked on I, nothing happened because it's already busy. You can also go here and interrupt kernel. Let's see if I can. Yeah, you can interrupt kernel here. But anyways, let's let it be. We will come back. So let's estimate this integral using the method we learned. What is the method? F of x, you take the mean of this. That's it. B minus a times the mean of this, if you can remember. That's the Monte Carlo method. So, oh no. First, we're going to apply the same method we applied here. Area of square times, oh yeah. So what does it say here? Oh yeah, we interrupted. Let's decrease, let's make it maybe some few thousands. All right. Let's see if this one yields 3.1. So this is 3.13. It's not yet 3.14, but anyways, you see that increasing the number of points. Here we want to integrate this. You remember, we need f of x max minus f of x min times 0 minus 1. That is the area of the square which we want to put this function in, and then we are going to randomly generate values in the y-axis and in the x-axis, and those in the y are between f min and f max. Those in the x-axis will be between 0 to 1, and we are going to apply the same method. So it's b minus a times number of in is k. Here, number of points that fall in within the integral are k, and n is the total number of points. You're going to look at this function because you can assume y equals f of x. So the maximum you can have, f of max is 1 when x is 0, and then f min is 0 when x is 1. So they're almost, and therefore the integral here will be b minus a times 1 minus 0, which is automatically b minus a, times number of inside divided by the total number. B minus a is also 1 because 1 minus 0, and in the end your integral is just k over n. K over n is easy to do. So you just count how many are in, you divide by the total number. Yeah, so here we declare the function, but this x, we know that we're going to sample it. Define your a, define your b, define your total number of points, generate random x from the from zero, sorry, from A to B, and then generate random y from f min to f max, and that's it. And then you set the condition. And the condition is, if the value we generated here, because you're going to take any arbitrary points between here and here. So for any arbitrary points between here and here, let's say xy equals 2 comma 3, if that value of y is less than or within the range which f of x exists, it should be counted as inside, else outside, just like we did in the previous cells. And therefore you sum all the insides, and that's it. And then you do number of inside divided by total number times the area of the box, which obviously is b minus a times 1 minus 0, and that's it. That's the integral. And what do we expect? This is the estimated, and this is the true value. The second and most efficient method is the one you take the mean. I did not do that one, did I? Yeah, oh yeah, okay, I already explained. That's the first one. Okay, so alhamdulillah, thank you.